Hello, welcome to this lecture on biomathematics. We have been discussing ideas from statistics that are useful to understand various biological phenomena or the various things in biology. In this lecture, we will learn something that is pretty much used every day in laboratory. That is something that you all do in laboratory is, or we all do in laboratory is basically take some experimental data, you get some data points and you fit some curve, you either fit a straight line or some curve. So, and you use these days you use computers, you just give the data to a computer using an Excel sheet or various other softwares. You just give the data, click somewhere, fit a line, it will just give you a nice straight line that fits to the data. But what is going on behind the computer? What is the principle behind this fitting? How do they fit it? So, that is the question. So, essentially we will be finding out how do we fit a function to an experimental data. So, under the statistics, our title for today is fitting a function to experimental data. So, that is essentially what we are going to discuss. So, now let us go back and let us think about a typical situation in a lab. What happens? You do an experiment, you get some data. So, this is something that typically you get. So, you get some points. So, there is, by looking at this point, before concluding anything, like before knowing anything about this, some tendency is basically to join the data points. So, is it fine to join data points like this? The answer is no. It is not, it is incorrect to actually join the data points just with some curve like this. It doesn't mean anything. So, one has to know some idea about what this data points must be to really to fit. So, first of all we have to know whether this will be a straight line or this is what is the function that you need to fit to this particular data points. So, for that you have to know something about the phenomenon going on behind this experiment, what is actually going on. So, basically when we get some data points like this, first we have to know what is going on behind this experiments, what is actually the phenomenon is. Depending on that we can make some guess or we can know sometime that whether what is the function that this must be following, and if you know the function you can fit that function to this data. So, let us take the example of polymerization of actin, which we discussed in the cases, or polymerization of any polymer for that matter. Actin, microtubule, there are many polymers in biology, and this is some simple example to imagine. There is nothing complex there. So, I just wanted to point out that I want to take this example because it is very easy to imagine. So, as we discussed some time ago, like in some lectures in calculus, we have been discussing some simple things about polymerization of actin. So, what happens is you have a filament and you can either polymerize or depolymerize. So, you can polymerize with some rate Kp, we can depolymerize with some rate Kd. So, you have only two events, polymerization, depolymerization. Now, the question is what is the speed or the velocity with which this filament will grow? What is the growth speed, or what is the speed with which this filament will grow or shrink? So, the growth velocity or speed can be written as Kp minus Kd. What is the polymerization rate minus the depolymerization rate? Now, what is polymerization rate? Polymerization rate is actually proportional to the free monomer concentration. So, as we said some time ago, if you look at here, like you have a container and you have a filament and you have a lot of free monomers. If there are no monomers, this will not polymerize. If there are a lot of free monomers, it will polymerize faster. So, the polymerization rate is proportional to the concentration of free monomers. So, I represent C concentration as C, of where C is the concentration of the free monomers. So, I can write Kp, the polymerization rate, is some constant K0 times the concentration of free monomers. So, that is what is written here. Kp is K0 times C. So, I can substitute that here. So, the velocity of the growth speed can be written as K0 C minus Kd, where Kd is the depolymerization rate. So, this is the simple formula that you can get for polymerization speed, how the polymerization speed is related to the concentration of free monomers in the solution. The more free monomers, the more polymerization will happen. Now, you can plot a graph between V and C. What do you expect? So, this is like y is equal to mx plus c. If you can plot V along the y axis and C along the x axis, what you get is a line like this. So, this is V is equal to K0 C minus Kd. So, where C is the concentration of free monomers and V is the speed, you essentially expect a straight line, and the slope of the straight line is the K0, which is the intrinsic rate of polymerization, and the y intercept will be like Kd. This is something we already mentioned. So, let us imagine that you are doing an experiment of polymerization of a filament, and what you are measuring is the speed of polymerization as a function of concentration. So, this is what you are measuring in the lab. Let us imagine that you are measuring the speed of polymerization of a filament as a function of free monomer concentration. And you know that, so essentially from the physics of it, or from the science, if you look at the science kinetics behind it, we can know that essentially the polymerization kinetics will have so it is a straight line. If you plot V versus C, it is a straight line. For every value of C, the V, if you plot it, it has to be a straight line, because this is the formula. So, we expect this to be a straight line theoretically. So, theoretically we know that this should be a straight line. So, we have this particular data point and we know that this should be a straight line, but how do you get a straight line from this data? So, what we have is now is just data points. If we have such data points, how do we get a straight line from this? So, essentially what we have is essentially some points, experimental data points here and there. Now, from this we have to get a nice straight line. That means you have to know something about the slope and something about the y intercept. So, you have to know two parameters, the slope. So, we have to know two parameters to get the straight line. We have to know the slope, you have to know the y intercept. If you know these two parameters, you can get a straight line, and for some value of slope and some value of the y intercept, this will fit precisely to this experiment. It will fit very nicely to the experimental data. So, the aim, what is software? The softwares that you use typically, what they are doing? What they are doing essentially finding a straight line, finding slope and y intercepts such that it nicely fits. So, when I say nicely fits, what does that mean? So, there is a specific meaning for when I say it fits very nicely. Something is fitting very nicely to the data. There is a specific meaning, there is a precise meaning mathematically. So, we will see what today, what exactly we mean when we say that something is fitting precisely, something is fitting nicely, or when we say best fit. So, the best fit means that there is some mathematical meaning for this. So, we will come to that in a few slides, but at this point I want all of you to understand that if you have a set of data and if you know what is going on behind this experiment, that is if you know this function, whether it is the data is expected to be theoretically, whether the data is expected to be a straight line, or if it is a parabola, if it is an exponential curve. If you know this particular function and if you have a set of data, we can typically fit this data to this function, and how exactly we do that we will discuss in a minute. But at this moment we have this data, and here we are taking the example of a actin polymerization. So, from this example we expect that if you plot V versus C, we expect that V is equal to K 0 C minus K D. So, we need to know two parameters K 0 and K D. If we know these two parameters, I can plot a straight line. So, that is what essentially we are saying here. To get a straight line from this data, we need to find a K 0 and a K D that will fit the best way, that will nicely fit to this data points. Ideally, in an ideal case, we will expect all of them to very nicely go on top of each other in a straight line, but this is not what the reality is. So, we have to say something is best fit. How do we define best fit? How do we define nicely fit? So, what do you expect from the common sense? So, what we have here is that, what do we have here? We have, for every x value there is a y value. So, there is a data point here, for another x value there is another data point here. So, this is x value, there is a y value. For every x value, so there is a next x value, there is another data point here. For a given x value there is a y value, there is another x value, there is a data point here. So, for each x value there is a y value. So, essentially what you have is a table x, which is the C, the concentration here, and the velocity. For every concentration there is a velocity value you get from experiments. So, essentially what you have is a table here. The table look like this. So, look at here. For this is for every this experiment, this table you get from experiment, that is, for there is a Ci and a Vi. There are like I is data, there are 1, 2, 3, 4, there are 10 data points. So, I represents first data point, I is equal to 3 means third data points. So, that means this particular point. So, this is first point, second point, third point. Third data point is this. So, for every value of I there is a Vi. Now, if you know this Kd and Kc, so what we have here is for every concentration experimentally you have velocity. So, this is for one concentration value, another concentration. So, let us take a few points. So, for each of this concentration there is a particular y value that you get from the experimental data. Now, for theoretical curve, let us say the theoretical curve goes something like this. Let us say we get a best fit, which is something like this. Let us imagine here also for every C value there is a y value, which is, this is theoretical. Whatever I show in circle, that is a theoretical value. Whatever I show as dot, the field circle, this is experimental value. So, these are experimental values. this is experimentally you got, and this must be the theoretical value, because when we finally get a straight line, so let us say for actin, if you know K0 and Kd, you can get this straight line. So, you get this theoretical value. So, we have a theoretical value and an experimental value, and in the ideal case, in an ideal scenario, what do you expect? What do you expect is that in an ideal case, what do you expect? You expect that theoretical value and experimental value will be exactly on this case, on each other. That means, they will just exactly fall on the straight line, but this is an ideal case. But in reality, it will not exactly fall on the straight line, they will be slightly deviated from the straight line. For each point, this will be deviated from the straight line, here this will be deviated, some other point here. So, the theoretical value is this, experimental value is this. So, this deviation will be this. For some other case, here also the deviation is this. So, sometime, so for each experimental value will have some deviation from the theoretical value that you will get from the best fit. So, what we want is that we want the measured velocity and the theoretical velocity, the difference between these two should be minimal. So, you should minimize this difference. That is what common sense will tell you. When something is a best fit, when something is nicely fitting, there will be little difference. The difference between the measured value and experiment theoretical value should be the fit value, the fitting value. So, when I say V theory, this is the value, the velocity which you get from the fitting. That means, this line you have. So, for every C there is a value on the line represents a value. So, this fitting the value we get from fitting and the measured value should be, there will be some difference, but this difference should be minimal. So, what we expect? We expect that V experimental minus V fitting, this has to be minimum. So, if we define this as some function r, this function r has to be minimum. So, now what is experimental value? That is the points. So, V experimental is Vi, we have this Vi we have here in this table. Look at this table, this is our experimental value 12, 14, 13, 33, these are the experimental values. There are 10 experimental values. So, if you look at this graph here, so the experimental values we represent by some so now this is the theoretical value corresponding the fitting value is what you get. This is the fit value from the fitting, right. For each point there will be some value for the fitting. So, this difference here, this is this difference should be minimal. So, Vi minus what is the theoretical value? So, Vi is the experimental value, the theoretical value will be K0 Ci minus Kd. This is the value we get from fitting. From fitting we get that V fitting is K0 Ci minus Kd. If we know K0 and Kd, we can get this Vf. So, Vi minus Vf should be minimal, that means Vi minus this has to be minimal, but for every value there is a difference, and this all the total difference should be minimal. But if you look here, some of these are positive, this if you subtract this from experimental value and you will get a positive number here, here you will get a negative number, because this is more and this is less. So, the sum of this, typically sum of positive and negative, you expect this to go to 0. So, if we just minimize this sum of this, you get 0. So, what we want is that the better way will be to minimize the square of this. That means, if we minimize sum over I experimentally measured V I minus theoretically, or by the V I we get from the best fit, the difference square I is equal to 1 to n, where n is the number of data points. So, if we minimize this particular function, let me call this function as R. So, this function R, if we minimize, we get this value for k 0 and k d. So, we know that mathematically, if we have any function, the minimum of that function can be calculated by. So, if we had a function f of x and if it had a minimum here, if you calculate del f by del x here at this particular point, del f by del x will be 0. So, if you have a function and if you want to calculate the minimum, what you do typically is to find the derivative. So, if you find the derivative and equate that to 0, you will get that particular point where the function is minimum. So, we can do exactly the same thing here. What can we do? So, essentially what we want this R 0, which is a function of k 0 and k d. This R 0 you want to be minimum, which is V I minus k 0 C I minus k d whole square. This is the difference between experimentally measured value and the fit value. The velocity got from fitting and the velocity got from experiments, their difference should be minimum. So, that is the best fit should be this fit where this is minimum. So, if we do that, if we find the minimum of this, that is, we can find the derivative of this with respect to k 0 and k d and equate this to 0, then you will get the minimum of R. So, essentially what we want to do is that we want to find a certain value of k 0 and k d such that del r by del k 0 is 0 and del r by del k d is 0. So, this is what essentially we want. We want certain values of k 0 and k d such that their derivative is minimum. So, how do we do that? How do we calculate the derivative of this? So, let us look at this function we have here. So, what is the function we have? We have R is equal to V I minus k 0 C minus k 0 C I minus k d whole square. Now, let us look what is. So, this can be written as V I minus k 0 C I plus k d whole square. Now, we want first let us do del r by del k 0. What is del r by del k 0? So, surely there will be the whole thing is a square. So, there will be 2 times this particular function V I minus k 0 C plus C I plus k d. So, do it yourself this derivative carefully. So, this is the function and find the derivative of this. So, this square is this and the derivative of this. So, derivative of k 0 will be a minus C I. So, there will be a minus sign and there is a C I. So, this is del r by del k 0. Now, what is del r by del k d? What is del r by del k d? So, del r by del k d from whatever this is can be written as del r by del k d. So, if you know this particular V I, if you know this particular R, So, this is our R. We can write del R by del K D. So, there is same way there is 2 times this function, which is V I minus K 0 C plus K D, and that is it. K D as a constant. So, derivative of K D is 1. So, the only is a matter of just 1. So, this is what it is. So, you can find that del R by del K 0 is minus 2 times C I times this, and this is del R by del K D is 2 times V I minus K 0 plus K D. So, this both are equal to 0. So, this we want to find out the value of K 0 and K D for which these 2 equations will be 0. So, essentially this is written in this particular way. So, del R by del K 0 is minus 2 times V I minus K 0 C. If you take this bracket here minus outside, you can write in this particular fashion. So, do this yourself and see whether you are essentially getting this particular answer or not. Equal to 0, you get this. So, this is 2 equations and 2 unknowns. So, let us rewrite this a little more carefully. Let us rewrite this. Sorry, there is a sum over I here, which I have forgotten here. There is a sum over I everywhere. There is a sum over I here. So, just like you can see a sum over I here. Okay, so, what we get is 2 equations. So, let me write these 2 equations little more carefully. So, the 2 equations are minus 2 sum over I V I minus K 0 C I plus K D into C I equal to 0 minus plus there is a plus 2, if you wish, plus 2 into sum over I V I minus K 0 C I K 0 C I plus K D equal to 0. So, these are the 2 equations, and you have 2 unknowns here. The 2 unknowns are K 0 and K D. So, you have 2 equations and 2 unknowns. So, this is one so this is unknown. So, 2 equations and 2 unknowns. So, if you have 2 equations and 2 unknowns, you can solve this. So, you can take this inside, you can take the sum inside and rewrite this in a particular fashion. So, how do we rewrite it? So, if we rewrite this and rewrite the sum, what you essentially get is something like this. You can write this n K D plus K 0 into sum over I C I plus equal to sum over I V I. So, let us look at here this. So, the first term 2 I can divide both sides by 2. So, something divided by 2 by 0 is 0 by 2 is 0 itself. So, the 2 goes away. Then I can take this sum over I V I to the other side. So, what we have here is, and there is a minus sign here. So, there is a minus V I. So, I can write this as sum over I V I, in I goes from 1 to n, and there is K 0 C I in this, there is a minus sign. So, there is K 0 into sum over I C I and K D into sum over I, this is sum over n times. So, sum over I up to n is n. So, we have minus K D times n. So, you can write this sorry, yeah, you can write this. Okay, there is a Ci here. So there is a Ci here. So you have to take care of the Ci also. So there is, when you multiply the Ci with this K0, you get Ci square, and when you multiply this Kd, there you will get again a Ci everywhere. So essentially you get Vi Ci here, and you get sum over I Ci here. So you get sum over. So essentially what you get is this particular equation here. What you get is Kd into sum over I Ci is K0 Ci square into Ci Vi, and n Kd plus K0 sum over I Ci is sum over I Vi. So if you know this, if you know the sum over I Ci from the experimental table, we had already this table with Ci's and Vi's. So if you go back here, we had this particular table with Ci's and Vi's. From this particular table, it is easy for us to calculate sum over I Ci. It is easy for us to calculate sum over I Vi. It is easy for us, again this is sum over I Ci. It is, we can also calculate sum over I Ci square. We can also calculate sum over I Ci Vi. Just sum over all the x axis numbers in the first row, in the first column, sum everything in the second column. So this all essentially some numbers. So sum over I Ci is a number, because this sum of 1 plus 2 plus 3 plus 4 plus up to 10. So this is sum over I Ci. Velocity is also a number, so you can sum over everything, velocity, the column, the second column you can sum from the experimental data. So you can get this from the experimental data, you can get this from the experimental data, you can get this from the square and sum experimental data, you can get this from experimental data. N is also a number, how many times you did the experimental, so 10 times. So this all some numbers. So you essentially what you have is that sum A into A1 into K0 plus A2 into Kd is equal to A3, and B1 into K0 plus B2 into Kd is some B3. So essentially two equations and two unknowns, and A1, A2, A3, B1, B2, B3 are some numbers which we can obtain from experimental data. So we know A1, A2, A3 from experimental data, B1, B2, B3 also from experimental data. Then we can solve this equation, two equations and two unknowns, and we can write K0 and Kd in terms of this A and B, something in terms of this A and B. So this is what essentially they do in the computer. So what do they do? So what do they get? They get Kd is equal to sum over I Vi into sum over I Ci square minus sum. If you do the algebra properly, you will find that Kd is equal to sum over I Vi, sum over I Ci square minus sum over I Ci minus sum over I Ci Vi divided by n times sum over I Ci square minus sum over I Ci whole square, which we can rewrite in this particular fashion. You can just rewrite this a bit if you wish, because you can write this as Vi average and so on and so forth, just a different notation. So this is average V, average C. So you can write all this in a different notation of averages, and we can rewrite this expression in a different way if you wish. So then you get this particular experimental particular value for Kd. Then we can similarly we can get some value for K0. We can say that K0 we can find from the algebra, if you do the algebra properly, we can find that K0 can be written as in terms of this experimental data, which is Ci's and Vi's. We know Ci's and Vi's. So known Ci's and Vi's, we can get K0 also. So, essentially we can get k 0 and k. So, we can get, if you know the Ci's and Vi's, this is essentially the experimental data, we can get k 0, which is some summation, some combination of Ci's and Vi's, and k d is also some combination of Ci's and Vi's. And if you know this experimental data, we can plot the curve that fits the best as V fit is equal to k 0 C minus k d. V f is equal to k 0 C minus k d. You can find out a straight line which will fit the best way. So, some particular value of k 0 and k d you can find which will be the best fit, because the deviation from the total deviation from the experimental data and between the experimental data and the theoretical, the fit data is minimal. So, we minimize this deviation so that we get the best fit. So, known the constants, we can draw a line. Okay. So, we quickly discussed actually, known the experimental curve, how do we fit this data. So, the same thing can be applied to any function. So, let us say you have some other function. So, this R sometimes is also called chi-square. So, this is sometimes called chi-square fit. So, chi-square is essentially, if you have an experimental data, an x axis and a y axis. So, for every, so let us say there is for every xi value, there is a y of xi. This is experimentally measured y of xi. This can be some curve, it can be some data like this also. So, it might be like fitting with some, need not be a straight line, it might be fitting with a curve, some function f of x, which could be, so let us say a e power minus b x square, it could be even a Gaussian, or it could be any function, it could be a x square. Here this looks like a x power n, some in general some function, it could be any function. So, chi-square is the experimentally measured y data minus this function which is the parameters a, b, c, etc. You can write these parameters. So, this difference square, this is typically called as chi-square. So, chi-square is the experimentally measured function minus the function that will fit the data the best way. So, this will be a, b, you can have any number of parameters. So, in our case we had k 0 and k d, you can have any set of parameters. If you find this difference and square it, this function is called chi-square, and you minimize this chi-square with respect to a and equal to b, equal to 0, you can minimize with respect to b equal to 0. If there is a c, you can minimize with respect to c and equal to 0. So, how many of our parameters you have? A, B, C, this is like k 0, k d and all that. You differentiate with I equal to 0, you get that many equations. You can solve these equations and get the corresponding a and b that will be, for which this will be minimum. So, this is the idea. So, this is what is going on behind the experimental, behind the computer. This is what computer is essentially doing. It is easy to do for a straight line, it is little more difficult if the f of x is a complicated function, but essentially this is the idea. Now, where is this idea coming from? Why is this particular difference in square? Where is this coming from? Why this particular deviation being taken? So, let us think about it a bit more deeply. Where is this coming from? So, let us think about theoretical point versus experimental point. Like what do we expect? So, let us say we had this example velocity versus concentration, and if you for actin monomer, if you do polymerization of actin, V is K0 C minus Kd. It is known that K0 is about 11 micromolar inverse second inverse, that is K0. Kd is depolymer is typically close to 2 per second, it is like 2 per second. So, theoretically what you get is just a given these two numbers you can draw a straight line. Now, if you do an experiment for this particular value of concentration, if I do an experiment I might get a point here, if you do an experiment you might get a point here, if somebody else does an experiment they will get a point here. So, if you let us take the example, let us take even a simpler case. So, let us take this particular value C is equal to 1 micromolar. So, this is C is equal to 1 micromolar. What is K0 C minus Kd? It is K0 is 11. So, 11 into 1 is 11, 11 minus 2 is, so this has to be 9. Theoretically this value is 9. When C is 1, theoretically the value is 9, but if you do an experiment I might get the velocity 9.1 monomer per second, somebody else might get 8.9 monomer per second, somebody else if they do experiment they might get 8.8 monomer per second, somebody else might get 9.2 monomer per second. Now, you might get, if you do 100 experiments or 1000 experiment, you might get, if you fix the concentration as 1 micromolar and look at what is the growth speed of actin at 1 micromolar, you might get different values if you do this experiment. If you repeat this experiment 100 times, what are we doing? We are fixing C is equal to 1 micromolar and looking at what is the growth speed of actin, and I do experiment 100 times or 1000 times, each time I get some value around 9. Sometime I get 9.1, sometime I get 9.2, sometime I get 8.8, sometime I get 8.9. So, now if I plot the value of V I got, so this what do I get? I might get some Gaussian like distribution like this. This is like I meant to draw a Gaussian like a normal distribution. So, this is 9, we expect to get 9 monomer per second. So, most of the time you will get 9, some of the time you will get 9.1, some of the time you will get 9.2. So, the probability of getting 20 or the probability of getting 0 is very small. So, we just said that if you can expect or you can imagine that the deviations from 9 will have, the values will have a normal distributions like this. So, the experimentally obtained value and the theoretical value or the expected value or the best fit value, the deviation of this. So, if you can find the deviation from this, but if you plot this, if you find the distribution of this measured value, you can expect to get a normal distribution or a Gaussian distribution. So, what is the function? What is the formula for a Gaussian distribution? We discussed that the formula for a Gaussian distribution, the probability that you will find the velocity V I is proportional to e power minus V I minus some other V whole square divided by 2 sigma square. So, this is what you expect. So, where V is some kind of an average value. So, this was 9, sometime you will get 8.9, sometime you get 9 point. So, this is, if you could draw a Gaussian like this is 9, this is what you expect to measure the average value, but you will get a distribution like this. So, this is the expectation. So, now if you want, so basically what we want is to maximize this particular likelihood of getting this particular V I. So, now this is for a particular measurement. You can say that for all measurement, for different values, you can expect this distribution to be a Gaussian again or a normal distribution. So, now what is happening is you are maximizing this P. So, maximizing this P is like, it turns out that it is like minimizing this difference. So, what we did is minimizing this difference, which is like maximizing this probability. So, this is the basic understanding of this, but I do not want to go into the details of this too little. I do not want to discuss this in detail why exactly this is coming, but it is just to hint or direct you or to just to point out that where is it all coming from. But even from simple like some kind of a rational common sense, it is clear that what we would need is the distance, the difference should be minimal. Okay. So, what we essentially, so the deviation has to be minimum or it is equivalent of maximizing the probability. Even though I said about this particular case here, this is particular for a given experiment, you might get a distribution of in this particular way, but even you can extend this to the case of deviation, and even the deviation will have such a Gaussian distribution, and the probability you can find that essentially what you end up is minimizing the deviation is what essentially you end up is like maximizing the likelihood. But if there is time, we will discuss this in another lecture, but for the moment it is enough to realize that at the end of the day, essentially what all these computers, when they fit, what they are doing is essentially they are minimizing this function called chi-square, which is the measured value minus the fitting value, which is a function of the parameters square. And this you can do mathematically by finding the derivative del chi square by del A and del chi square by del B and equating them to 0. So, this is basically the summary of this lecture, that to fit a straight line or to fit any experimentally measured value to a fitting function. So, this is the experimentally measured value, this is the fitting function. You have to minimize this difference, and this difference can be minimized in this particular way. So, there is a sum over I, you have to minimize this particular function, and this can be done in this way, and that will give you A and B. So, with this we will stop today's lecture. So, this is essentially today's lecture was about fitting a line or a function to a experimental data. So, with this we conclude today's lecture, when we will discuss more about statistics in the coming lectures. Okay, bye.